Welcome back. So today we're going to be talking about how to use double integrals to calculate the surface area of the graph of a function of two variables. So let's go ahead and get started. So we have some function f of xy over some region R in the xy plane, and over that we have the graph of some function f of x, which is doing something up there. The question is, how much surface area does this graph take up? How could we calculate something like that? The answer is to calculate a double integral. The area of the surface can be found by integrating over the region R the square root of 1 plus f of x, f sub x squared, the partial derivative, plus f sub y squared, the partial derivative. Now compare this with the formula that we had back in Calculus 1 to calculate not the surface area of a surface, but the length of a curve. The arc length is what we called it. So this is a thought bubble. We had integral from a to b, the square root of 1 plus f prime of x squared dx for arc length. And this is a natural extension of that. Instead of just adding one derivative squared, we're adding as well the other derivative squared. And instead of a single integral, now we have a double integral to calculate the surface area as opposed to the one-dimensional arc length of the function. Now I have a warning here, and it's the same warning that I always give when we're calculating arc length in Calculus 2 or Calculus 1. The warning is that the square root over a plus sign, if the square root is over a plus sign, there's really not much that you can do to simplify this at all, except if you're lucky. So in general, these integrals are pretty hard to calculate, and the problems that you will encounter have been manufactured, I will say, contrived, to make them actually possible, because there has to be some trick that you can use in order to take 1 plus f sub x squared plus f sub y squared and actually manipulate it and work with it until you get to a point where you can actually calculate this integral. Let me give you an example. Find the area of the part of the paraboloid lying under the plane z equals 16. So we have our quintessential paraboloid here. Which is given by the equation f of xy equals x squared plus y squared. And we have this flat constant plane here at the level z equals 16, which intersects this paraboloid in a circle shape. So the part of the paraboloid that we're interested in is the part underneath that circular intersection, which corresponds to a region in the xy plane, which is underneath that, creating almost a shadow shape, a disk. So I'm going to call this R. Now to figure out the exact specifications of the region R, let's consider where the plane and paraboloid intersect. So let's go in and let's see where these two intersect. Z is equal to 16 on the one hand from the plane. Z is equal to x squared plus y squared And so our region R is bounded on the outside by a circle radius 4. Whew, that got wild, didn't it? Right at the end, right at the end. There you go. So here we have the region R. Now because this R is circle shaped, I already have an inclination that we're probably going to end up calculating this double integral in polar coordinates. But I will leave that to the correct moment. I'm not going to get too far ahead of myself because we have yet to even determine what the integrand should be for our particular function. For our particular surface area calculation, we still have to calculate f sub x, we still have to calculate f sub y, and then we still have to square them and add them to 1 and put them under the square root. So let's go ahead and calculate f sub x. Do you remember how? We take the partial derivative of x squared plus y squared, treating y as a constant, and fy is 0 plus 2y. And so at this point, we now have the integral over r of the square root of 1 plus 2x squared, the derivative in the x direction, plus 2y squared, the derivative in the y direction. Now I'm seeing another hint that polar integrals might be useful here, which is the appearance of the quantity x squared plus y squared in the integrand. X squared plus y squared, I recall, can always be reduced to r squared in polar coordinates, so it might help me out a bit. Alright, I'm convinced. We're going to go ahead and we're going to calculate this double integral using polar coordinates. So let's set up the integral and let's transform the integrand to match that. For a disk of radius 4, the r goes between 0 at the center of the disk and 4 at the disk's edge. For a full circle, rather than a quarter or half circle, theta goes all the way from 0 to 2 pi. Now, instead of 4x squared plus 4y squared, I'm going to go in and replace every instance of x squared y squared with an r squared. And what am I missing? I am missing, of course, that extra factor of r that comes anytime we want to calculate a polar integral. And it's that r, actually, that saves us. Imagine how difficult it would be, actually, to calculate this integral if that r were not there. It's because the r is there that we unlock the ability to use a u substitution to actually make this first integral viable. So for example, we can set u equal to 1 plus 4r squared, so that du is equal to 8r dr. And we can go ahead and we can transform this inner integral. Integral 0, r goes from 0 to 4, into the square root of u, and then 8r dr, so we'll have 1/8 du. Alright, so now we get to integrate u, which has a power of 1/2. So by the power rule, this can be thought of as u to the power 3/2, then 2/3 comes outside. And this is being evaluated as r goes from 0 to 4. So let's go ahead and let's put back our values. 1/3, and instead of u, let's return to 1 plus 4r squared. From 0 to 4. So now when r is 4, when we plug that in, we get 4 times 4 times 4 plus 1 is 65. So far we are at the integral of 0 to 2 pi of 65 to the 3 halves times 1/3. And if r is equal to 0, then this back term vanishes, and we're left with 1 to the 3 halves, which is simply 1, and then times 1/3. So our integrand has become a constant, a complicated constant, but still a constant. And so we have 1/3, 65, to the 3 halves, minus 1/3, times theta, evaluated from 0 to 2 pi. And so finally, for our surface area, we obtain the quantity 1/3, 65, to the 3 halves, minus 1/3, times 2 pi. The surface area of this paraboloid. Quite amazing. There's not really any other viable way to calculate the surface area of something like a paraboloid. So this is an incredible tool.